And we are recording. Okay. So let's continue. So we answered the first part of this question. Now we're going to answer the remaining three parts. So now we want to check independence of random variable. So I'm going to write the definition. So two random variables, maybe I can say x and y are independent random variables if and only if for all pairs of values x and y in the range x and y respectively, we have the following equality. We have the probability that x is equal to x and y is equal to y is equal to the probability that x is equal to x times the probability that y is equal to y. So that's what we have to verify for every pair of values in the range of x and y respectively. Maybe I'll just make it clear, the range of x and the range of y. So the first thing that you should think about is what is the range of x, what is the range of y. Here the range is pretty easy. We're counting the number of heads and tails into flips. So here, if you think about it, the number of heads is directly related to the number of tails, right? So in your head, you're like, well, obviously these two things are not independent. But I think just the thing is, I don't know the marking scheme of the exam. I don't know what sort of answer you're expected to answer, but the safest thing that you can do for yourself is to use the definition of independence variable, even if the answer might be totally obvious just from the definition. So here, how do we use this definition here? Okay, well, I have to show that all of these equalities are true. So now if I'm going to show that they're not independent, well, the answer is, how do I do this? I just need one value of y, one value of x, such that this equality is not true. So can you guys give me two different values of x and y that will make this equality not true? Like two very easy ones. Actually, you have plenty of choices. Zero and zero is a valid choice. So if I take 0 and 0, then this probability is 0, right? Just the same reason. If x is equal to 0 and y is equal to 0, well, what is that probability? It's the probability of getting no heads and no tails. So that is 0. But this probability, x is equal to 0, is not 0. And this probability, y is equal to 0, is not 0. So, okay. So we can just use this example. Note, probability of x is equal to 0 and y is equal to 0 is equal to 0. Have to have some tail or some head. Also, probability of x is equal to 0. We just know what it is. This is the probability of tails, which is 1/4. And probability of y is equal to 0 is equal to the probability of which is 1/4. So you have 0 is equal to 1/4. What times 1/4? No, this is not verified. And y are not independent. And I know this seems like quite a bit of work to state something that is pretty much obvious. But the annoying thing is that it's kind of the safest thing to do in an exam. Like you might think that two random variables are independent and then surprise they're not, or vice versa. I think that two things depend on each other and surprise they don't. So the safest thing that you can do for yourself is to resort to the definition. If you stick to this definition and you do it properly, we cannot remove you marks. So again, since I don't know the marking scheme for this exam, I think this is the sort of thing that you should aim for. Even if here it's quite obvious that they are not independent random variables. Yeah, and actually 0 and 0 is not the only two values that work, right? You can think of plenty of the values. Right? If you, like someone said, so as long as the sum is not equal to 2, you're kind of doomed, right? If I take 2 and 1, that's bad. If I take 1 and 2, that's bad. If I take 2 and 2, that's bad. So there's plenty of values to pick from. Again, just even if your gut is telling me, well, I can write something in English that tells you that they're not independent random variables, you're correct. For the sake of being marked, just write this. And this is, we cannot remove marks from this. If you do it properly, that's the safest thing to do, in my opinion. Again, if suddenly like we do have a marking scheme and like the solution tells you, oh, well, note that this is directly a function of this and vice versa, then yeah, they do depend on each other. But here we don't know that, so we're just being safe. Okay, next are x and y independent random variables. So here, this is where some students try to write some English arguments and it doesn't work. Here, even if z is related to x, there is also y. So again, so you could think, oh, well, z is a function of just x, right? Because y is equal to 2 minus x. And the number of, if x is the number of heads, then 2 minus x is the number of tails. So z is equal to x times 2 minus x, which is just a function of x. And then you might be tempted, oh, well, z is a function of x, therefore they're not independent. Again, the safest thing to say is to check the equalities, and maybe the equalities just work. Right? So if you write the definition once, don't write it again. Just give two values if you can think of two values. So can you guys think of two values, one for z, one for x, such that this equality is not true? Yes, exactly. So remember, z can be 4. And if z is 4, then x has to be 2. So that is really the good counterexample to think of. So here, similarly, the probability that x is equal to 2 and z is equal to 4 is equal to 0. as z is equal to 4 implies x is equal to 2. But if I want z is equal to 4, it means that sorry, it's you said 0, right? Yes, or 1, for example. So the value that is not 2, obviously. So this is equal to 0, since z is equal to 4 implies x is equal to 2. And now we know probability that, well, actually we were pretty much done here, right? So we know each of these probabilities. But now we think, is there a problem with that? Or is there not a problem with that? What is the probability that z is equal to 4?
Yeah, it's 0.
It's 0, so it does work out. Okay, so this works. So what about this? This will also work. So what about this? This will also work. So when I put a z is equal to 4 here, I'm good. Okay, so now what happens when you put x is equal to 2? And that's, so the point here, usually how we come up with the counterexample, the trick that we give you is, I think, try to make this side 0, right? And then this side won't necessarily be 0. But it's valid in the other way. If I put z is equal to 4 here, I get a 0 on the right-hand side. But is this probability 0? And the answer is yes, right? Here we get 0 is equal to 0, so it doesn't really work out. Someone said z is equal to 1, x is equal to 1. So what happens? So so does that work? If x is equal to, so you guys have some suggestion, right? So if x is equal to 1 and z is equal to 1, what is that probability? So here, my question is, what is this? Is this 0 or is this not 0? Which one is it? Does this one work or does this one not work? Which one is it? So what is that probability? Is this one 0 or this one? Well, what I wrote here was for x is equal to 1, right? So this one is 0, and we don't care about that. So now here, if I put a 2 here, is this one 0 or not? No, right? So this one actually does work. So the point is that on the right-hand side, sorry, I keep thinking it's higher than this. So on the right-hand side, I'll have 0, but on the left-hand side, I won't have 0. So this is the probability that x is equal to 2 and y is equal to 2. So is it 0 or is it not 0? It is 0. Okay, good. We can move on. What about the probability that x is equal to 1 and z is equal to 1? Now this one works, right? Probability, this is equal to the probability that x is equal to 1 and maybe I'll write and, well, it doesn't really matter, and y is equal to 1. What is this? Well, this we know already. But this is just a half. Actually, if you don't even need this part, right? You can just say this. That this event is contained in this event. Or is it the other way around? Which one is it? So here I'm trying to confuse you. So which one is contained in the other? Is x is equal to 1 contained in this one? Or is this one contained in this one? So there's several ways to argue this. Just be careful. They mutually contain each other. An interesting statement. So like a hug, not exactly, but so no, they don't mutually contain each other. One contains the other, or I should say, one implies the other, but not the other way around. Exactly. Here, the correct intersection is this. If I know that z is equal to 1 and x is equal to 1, then z is equal to 1 already tells me that x is equal to 1. So the smallest guy is actually this guy. This guy is contained in this guy. If I know that x is equal to 1, I don't know that z is equal to 1. So the probability that z is equal to 1 is a half. This is something that we found earlier. So you don't need to justify it again. Okay, so we have a half. Now what is the probability that x is equal to 1? Well, like we said above, the probability that x is equal to 1 is a half. But it's the probability, if we do it again quickly, it's the probability of one head, which means tail heads or head tails. Now the probability is that,
like in the first inequality, why do we have probability of x to be 2 and y to be 2? Like why does the equality hold?
here, from there to there?
Yes.
Okay, so if z is equal to 2, what do I know? Again, we're not using this, but it's a fair question. So if z is equal to 2, what do I know?
Yeah, if z is equals to 4, then y is 2.
Sorry, if z is equal to 4, then what do I know?
Y is 2 and x is 2.
Exactly. And so x is equal to 2 and x is equal to 2 and y is equal to 2. That just abbreviates to that. And actually, if you don't like this, I could just have written z is equal to 4. That's the same thing. Again, it's the same idea. If I know that z is equal to 4, then it implies that x is equal to 2. So this guy is contained in this guy. So the intersection of both is the smallest guy. So it's z is equal to 4, which is 0. And now you see that they're not independent, right? I have a half is not equal to a half times a half. Again, you could have thought about this just in terms of, well, z is a function of x. Right? Z is equal to 2 is equal to x minus times 2 times, sorry, oh man, x is equal to x, z is equal to x times 2 minus x. Sorry about that. Now you can use the same example for x, y, and z, right? Z is also a function of y. Z is equal to y times 2 minus y. So these two random variables will not be independent. And if you want to stick to the definition, you can use the exact same example. Replace a y here, replace a y here, replace a y here, you get the exact same thing.
So now how did we disapprove the last statement? Because I don't see the inequality that's being held.
Sorry, this last statement here.
Yeah, how did we show x and y are not independent? Like what?
So we found two values. So this is equal to a half, right? This is equal to a half. This is equal to a half, and the probability of z is equal to a half. Z is equal to 1 is equal to a half. So I don't have that a half is equal to a half times a half. Essentially, switch the y for z here. So when I put x is equal to 1 and z is equal to 1, is it equal to x is equal to 1 times z is equal to 1? And the answer is no. This is a half. This is a half times a half. So I don't have. And yeah, so z is x times y, right? But y is a function of x. Y is just 2 minus x. So actually z is just a function of x. Actually z is just a function of y too. So again, it's if you understood this part, it's the same thing that we did here. It's just I did not rewrite the definition. That's it. So the principle is we found two values such that these products are not equal, right? This right hand side is not equal to the left hand side. Now, same argument for y. So it's the exact same thing. So again, the point of looking at this question is to just, in the exam, that's how I would write this. I think it's the safest type of answer that you can give. Even though you can look at this function and think, oh, well, yeah, they're clearly not independent. Okay. So if you didn't like this question, which I didn't like, but still did it for a reason. Now let's look at this one. So again, our two random variables independent. So what I do, I always start with my definition. So I write my definition. So I copy and paste it. So you state what the definition is, and that kind of gives you mark from the get-go. Means that you at least know what you're talking about. Now, we're trying to check with this definition, this x and y are independent random variables. Okay, so now let's think about the number of equalities we would have to check. What is the range of x? Here, what is the range of x? 2 to 12, yes. What is the range of y? Minus 5 to 5, exactly. So read the variable carefully. Right? X is the sum of two dice. What is the range of a sum of two dice? It's from 2 to 12. So it's not just one dice, it's the sum here. Okay, so again, this is not something that you write in your solution. It's just think about what this is asking you to do. If these two things were independent, how many equalities would you have to check? So how many values is there in there? From 2 to 12, that's 11 values. How many values is there from in there? That's also, how many values? That's 9, right? No, that's 11. Can't count. So that's 11. So how many equalities would we have to check if we wanted to show that they are independent? Too many, and that's exactly the point. That's 11 times 11 equalities. That's 121 equalities that you would have to check. There's no way in an exam that we would actually want you to check 121 equalities. So the odds are they're not independent, right? So that would make equalities. I think equalities, is it a word? It's probably not a word. It's probably my French brain turning this into a word. Is it a word? Is the word equalities actually?
Yeah, it's valid.
Oh yeah, okay.
Yeah.
And I would make 100 equalities to check. Isn't it equations? I don't know. Okay, so the point is, odds are these two things are not independent. So now can you think of values, two values of x and y that will disprove this? So two values such that this equality is not true. Yes. So sure. So what did you think of? So what was your reasoning here? So if this is equal to 0, then it means that the two numbers are the same, correct? Y is equal to 0, the two numbers are the same. When I add two numbers that are the same, I must have an even number. And that's why he came up with this example. Right? So if I subtract, if my subtraction here is equal to 0, means that my two numbers are the same. But if this guy is odd, then the two numbers are not the same. So for example, probability that, look at the probability that x is equal to 3 and y is equal to 0. Is that's 0. Why is that? Since if y is equal to 0, so there's several ways to argue this, okay? What I'm giving here is not the only way to argue this, but maybe the shortest way to argue this is to say the following. So since y is equal to 0 implies that I is equal to j. So x is equal to 2 times I, which is even. It's 2 times something. It's even. And you're done. So this is 0 because this implies this, which means that when you add these two things together, you get 2 times something, which is even. It cannot happen. And now, well, if you just conclude with these two other things, probability that y is equal to 0 is equal to what? If y is equal to 0, you have the same numbers. So that's 1 over 6. And the probability that x is equal to 3, that's 2 outcomes out of 36. Right? You get 2 1 or 1 2. So this is equal to 1 over 18, or if you prefer, 2 over 36. And so you know that your equality is not verified. 1 over 6 times 2 over 36 is not equal to 0. Or x and y are not independent variables. 2I means 2 times I. Right? That's why I don't like I, because it always turns into something like this. So I'll write, well, I have to write I, but here, really, if y is equal to 0, then these two guys are equal, which means that this becomes 2 times y, I. I could write 2 times j if I wanted. Exactly. So just be careful. It's not to get x, it's to get y. They both need to be the same in order for y to be equal to 0, which means that x is even. But here we selected x is equal to 3, so this cannot happen. So this one If you don't see this justification, again, this is not the only way to justify this. Right? You might think of different values. This is not the only example. There's plenty of other. But this is perhaps the shortest thing that you can come up with. See, I didn't talk about outcomes here, I just use math logic. All right. Next question, which looks scary. Is it scary? I haven't really read anything yet. Consider the following algorithm, which takes as an input a large integer n and returns a random subset of the set 1 to n. Okay, so what do? We flip a coin, and okay, so essentially it looks a lot like the first step in a skip list, right? If you guys remember skip lists, that's exactly what's happening, correct? Have you guys seen skip lists? Or I hope so. I think you're supposed to see skip lists. Oh, there's a nope, that's not good. Okay, if there's a nope, that's not a good sign. I'm pretty sure you're supposed to have seen a bit of skip lists. Oh, okay. So the idea of a skip list is essentially that is you have a list of elements, and then you create in several steps a bunch of subsets. And what you do, how do you remove elements from your set? Well, if your coin lands on tails, you did not include that element in your next list. But is this, you don't have to know that it's a skip list, but it essentially comes down to the first step of a skip list. So what do we do here? We're essentially flipping one coin for each element, and depending on the outcome, we add this each element to our subset that we're creating. So if we get heads for 1, then 1 is an element of our subset. If we get tails for 2, then 2 is not an element. So this is what this algorithm is doing. So now what do? We look at two variables. These are random variables. So, well, no, they're not random variables, but anyways, we're getting to a random variable. So we look at these two values. So the maximum of A is the largest element in A if it's not empty. Otherwise, we set it to be 0, right? If I get all tails, then my set does not contain any element. So we do have to take care about this case. This is a possible case. Same thing for the minimum. If my set has an element in it, then we look at the smallest. Otherwise, it's 0. So if my set is empty, I set my minimum to be 0. So then we're asked to show we have this random variable, the maximum minus the minimum, prove that this expected value of the random variable x satisfies e of x is equal to n minus 3 plus f of n, where f of n is some function that converges to 0 when n tends to infinity. So it looks scary. Let's see if it's actually scary. So here, just focus on finding the expected value. Okay, that should be your focus. And for those that did a bit of math, what we're essentially doing here is we're kind of finding a Taylor series of this function. So we'll see what we need to use. So the first thing that we can understand, the first thing that you should be able to understand, So we're panicking, but let's not panic. Is what will I write here? What is the next line that I should think about? Yes. So you should think to use linearity of expectation. So I will use that. This is equal to the expected value of the maximum of A minus the expected value of the minimum of A. Okay, so now we deal with each separate expected values. So how are we going to deal with this one? For example, I want the expected value of the maximum of A. So now think about the definition of expected value. If you're not sure if you need to use indicator variables or whatever, if there's some trick to it, stick to the definition. Here you should have used linearity. But you have these two functions. It's simpler to look at them individually. So you should think to use linearity. Now think about what is this? So here I'm going to use the definition of expected value. So there's two things in there, right? So I don't know, let's call MA denote the range of max A. I could have called it something else, but I'm just giving it a name. So MA denotes the range of the maximum. By definition of expected value, I'm summing, and I look at what? I look at all possible values in my range. So I will take X. Well, maybe I won't use X. Maybe I can use K in MA. And take each value and I multiply each value by its corresponding probability. That's just the definition of expected value, right? You look at the range of your function, and you look at every value, you multiply by their corresponding probability. So that's just definition of expected value. Okay, so what next? So we have two things to think about. So what is the range of MA? What is the range of the maximum? So how small can my maximum be? It's 0 to n, exactly. So the range is just from 0 to n. Okay, and now we have to think about what is the probability that m, the maximum of A, is equal to k. Now, we've kind of dealt with something similar. So if my maximum is k, what needs to happen? Yes, you're allowed. If your set has only one element, it can be both the max and the min. It is both the max and the minimum of this set. So now, what is the probability that max A, the maximum of my set, is equal to k? So think about what does that tell you about the sequence? So someone said 1 over n. Not quite. So remember, we're not picking the elements at random. We're flipping a coin for each of them. Yes, so that's exactly what you should think about. It's what Stephen was written. So no, k is just some number from 0 to n. Right? K is in my maximum. So if you prefer, for any k in the maximum of a. So again, why am I doing it this way? Because you don't want to give some pattern argument. You don't want to say, well, okay, the probability that max a is equal to 0 is this value. The probability that max k is equal to 1 is equal to this. And then I can derive that the probability of max k is equal to something is this. You want to learn how to argue this regardless of the values of k. You don't want to make it a pattern argument. It's not a formal proof. It's not formal enough. So patterns help, but they don't serve as proof. So here, all I did is I picked some value. And now I'm going to show what is the formula for this specific value. So it's k. I'm getting a formula in terms of k. So the hard work is to justify this formula without specifying k. And the key here is exactly what was written in chat. The last successful flip was on k. Successful meaning the last head that I got was on k. If I get another head after k, then I got something bigger than k. That's not allowed. So here, it's the probability that what are we dealing with? It's the probability that the last successful, or I should say the last head, is at flip or on the kf flip. On the kf flip. Okay, so essentially, if you want to make a drawing, you have something like this. You have a bunch of things before, so a bunch of flips. Then at flip k, I got a head, because that's my maximum, so that maximum needs to be in my set. And then afterwards, I got a bunch of tails. So now you can think, or you should be able to think, what is the probability that I'm looking at here? So count this. Remember, this has length n, right? So the total number of sequences of heads and tail that I can make is 2 to the n. That is my sample space. Now, how many of these sequences have a head at position k and all tails after? That is my question. Zero to the 5. Yeah, so we're pretty much getting there, right? So here, this is position k. Well, almost there. So is it n minus k or is it something different? So how many flips is there in here? So k minus 1 flip, right? This one is fixed. This one is fixed. So here I'm looking at this number of flips. This can be anything. It doesn't matter if here it's head or tails. if this guy, if for this element, this is element k, this one is in it, my maximum is k, because I did not select anything bigger. So here anything can happen. So I don't have any restriction on these flips. So how many possible flips do I get? Well, it's from 1 to k minus 1. So I have 2 to the k minus 1 possible flips. And now if you simplify this, this becomes 1 over 2 to the, well, here I maybe, yeah, it's, so I'll just simplify it like this first, so it doesn't confuse anyone, including myself. K minus 1 minus n, which is equal to 1 over 2 to the n minus k plus 1. Yes, that's exactly what this means. The probability that my maximum is equal to k means that when I was flipping my coin, I got a head for k, but then I got a bunch of tails after, right? If k plus 1 I get a head, then it's in my set. But then my maximum would not be k, it would be k plus 1. So once I flip head for my maximum, everything after needs to be tails. So which means that this is a fixed outcome, this is a fixed outcome, so it's the probability that I got this. Did I just, so that's the reason. It's exactly that reason, because they're fixed. Okay, so essentially if I were to make this a tiny bit more formal, I don't like this. So what did I do here? So here you guys are probably tempted to use independence of the flips, right? Personally, I almost never use that. I prefer counting. So here, what did I do? How did we get to this equation? So what was my sample space? Sample space. It's a bunch of, it's a sequences of heads and tails of length n. And directly, I know that the size of S is equal to 2 to the n. Yeah, so now what is the probability that I'm looking at? Well, I'm going to count the number of sequences of heads and tails of length n for which the last head was on the kth flip. Again, this is the key to solving this question, right? If I know that the maximum is equal to k, then the last head that I got, what on the flip was on the kth flip? It was for element k. Otherwise, I would have something bigger. So we are
how did we get this? A half power n minus k plus 1.
So this part, if this is true, this is equal to that. You just inverse, right? This is a base 2, this is base a half. This part is just math. So if you don't like this part, there's another way to argue this. I personally prefer this way, but you could also have gotten this directly. And again, it all comes down to this drawing here. This is element K. This is position K. So at position K, I got a head, and everything after, I got tails. So if you want to get to there directly, to this equation, you just say, well, okay, I got one head and n minus k tails. And that's exactly what you're doing here. You got one head, so a half, times a half to the n minus k. So that's n minus k plus 1. Or you do a counting argument. You count the number of sequences in total that looks like this. And this is position k. So the number of sequences like this, where this is position k, is 2 to the k minus 1, because this is free. I have no restrictions here. Elements of, oops, I see. Elements of S such that so we're counting elements of S such that the kf flip head and after all tails. We only have two options. The first k minus 1 flips. So again, there's two ways really to justify this. Either you do a counting argument, which leads to this, or you say, well, okay, I'm looking at the probability that my kf flip was a head, which is a half, and all remaining n minus k flips, so the flips after my head, so not my first head, my last head. So the probability that this last head is, my last head is at position k is a half, and all the remaining flip is our tails. So that's 1 over 2 to the n minus k times this flip for the head. So the uniform sample space follows from the coin being fair. If the coin is fair, everything is uniform. So you don't have to state why it's. Yeah. Oh, thank you. So after this question, we'll take another break. So we're pretty much done, right? Well, almost done. So again, the key here is this line. Once you understand this line, it's not that difficult to get to this one of these expressions. They're the same. So you're probably going to end up using this one. And now you just plug this in your expected value definition. So the expected value of the maximum of A is equal to sum from k is equal to 0 to n of what? Of k times this thing here. Okay, so we'll take a break right now, and then we'll finish this question. But we're not quite done. We did the hard part, figure out what to do for the max, and then the minimum will be very similar. Minimum will be almost exactly the same thing, the same idea. So again, we're taking a break, a 10-minute breaks right now, and then we'll finish the question.